Okay, so I'm going to talk about labs 4 and 5. Um, got lab 4 up here, and for this lab, it's basically taking lab 3 and extending that so that we're um, looking at the all the terms in the thermodynamic equation, not just the horizontal temperature advection terms. And the idea of this lab is for you to create a document that I'm calling a how-to document that explains how to calculate the terms, all the terms in the thermodynamic equation using the software that we've been using for previous labs, in particular lab 3. And this document is meant to be picked up by another student in taking this class, someone who's had Synoptic Lab 2 before, someone who's had dynamics, someone's had thermo, but has had some experience with the software, and explains to them how to calculate, how to actually come up with estimates for the numerical values for each of the terms in the thermodynamic equation. So you need to provide enough detail that it's an explanation of these calculations, and also demonstrate these. So actually illustrate these calculations using data from a big storm that happened a few years ago, Groundhog's Day blizzard, that we have archived. So let's focus at 850 millibars and pick 2 locations for your demonstrations. One that has rising motion and the other that has sinking motion. So it's important to include detailed explanations of these methods. And so this this should be a fairly comprehensive document that will cover these topics. So since we're going to be using the software, make sure that your document explains not only how to calculate each term, but also how to use the software. So how to start the program, how to plot a skew T, how to set values like the grid file, forecast hour, vertical level, geographic area, how to set the contour interval for contour plots, how to set the colors, the fills for the color fills, wind barbs, how to overlay different types of plots, and how to display the variables that you need in order to do the calculations that you want to do. Make sure, again, look at 2 different examples, rising, sinking motion, and again, you're going to want to pick a location that has significant horizontal advection as well. You really want to be able to demonstrate these processes. So we're still looking at the thermodynamic equation. This is what we went through in lab 3. Again, this equation is a local time tendencies, the partial dt dt, the horizontal advection minus u dt dx minus v dt dy. Terms that involve omega are the work and the vertical advection. These are both included here, and then the added heat term. We can combine the work and the vertical advection together into one term. That's a little bit easier to use when you do calculations. So that involves the potential temperature and how that changes with pressure. And so we're really looking to show and demonstrate how to calculate each of these major terms: the local time tendency, the horizontal advection, the, I guess what I'll call the vertical velocity terms, and the added heat is a difficult thing to calculate. So usually what we do is calculate the other terms and add and subtract them and estimate the added heat as a residual term. So omega, remember omega is the vertical velocity in pressure coordinates. So it's just telling us how the pressure changes with time as we follow a parcel of air. If you're going to do any calculations with omega, you're going to want to get MKS units. So pascals per second is strongly recommended. Unfortunately, the software we use, both GEMPAC and EAPS, will provide that information in millibars per second. So you're going to have to do some conversion from millibar to pascals in order to do any calculations. Okay, and recall that a negative value of omega means that the parcel's pressure is decreasing and it's rising. And a positive value for omega, the pressure is increasing with time as it moves, which means it's sinking. So in order to estimate or calculate these derivatives, okay, we have all these different derivatives, either a time derivative or a spatial derivative or a vertical derivative. We're going to want to use finite difference approximations to do that. And so this shows a time series of temperature where we have values at specific times. This is typical for what we're dealing with the data that we have. Either observed data is available at specific time intervals, or say data from the numerical models is available at specific times. Well, we want to use these discrete times, these finite differences between temperatures at specific times in order to estimate the time tendency. Okay, partial dt dt. And there's different approximations to this that we can try and see what's going to come up with the best or most accurate estimate of this partial derivative at time t. So let's say we're interested in dt dt at this particular time. So really we're trying to determine the slope of this curve at this specific time and estimate that just using values at these discrete times, right? So where we have this little circle with x in it are the only times we have numbers available to us to make a calculation. So we can do what's called a backward difference and basically look at how the temperatures have changed before our time t. So take t minus t at earlier time divided by the little t minus t early. We can do a forward difference, basically look forward in time. So take the later temperature minus the earlier temperature and divide it by the time difference. Or we could do a centered difference. Okay, centered difference goes on either side of our time. So we take the temperature later minus the temperature earlier and divide it by the time later minus the time earlier. So which approach do you think is going to give us a more accurate estimate of the slope of this curve at time t. We can use a similar approach to do, say, a vertical derivative, like dt dp. And so if we want to use a center difference approach at this pressure, we would want to look at values at a higher pressure and a lower pressure, difference those and divide by delta p, and turn this partial derivative into finite difference, so delta t over delta p, in order to estimate the vertical derivative. So in order to do that, we're going to need to look at sounding data and get values of, in this case, potential temperature at different pressures, difference those in order to estimate the vertical derivative that is in the term that involves omega, right? So d theta dp. Or we could do it this way. We could do dt dp, and then we'd have to calculate alpha over cp in order to get these vertical velocity effects on the thermodynamic equation. So the rest of this, it gives instructions for using a thin link on Scholar. Went through this in Lab 3. These instructions are in the Lab 3 lecture video, and also in the documentation for the software that I put on the class webpage. So there's lots of information on here. It kind of goes through how to use Nmap2 and IDV and GEMPAC. Pretty much material that we've gone over in the previous labs is all contained in this documentation on the web page. Okay, so that's Lab 4. Again, it's focused on the thermodynamic equation using the GEMPAC or NA-WIP software, whichever one you're more comfortable with is fine. And make sure you provide detail on how you calculate each of these terms. Illustrate it with real numbers based on the 54-hour forecast from this Groundhog's Day storm. Okay, that's a GFS 211 file. All right, so we'll switch gears and look at Lab 5. So Lab 5 is kind of continuing along these lines, where we want to use software to look at data and calculate terms in the equations of motion. This time we're going to use Python, and we're going to focus on the momentum equation. Okay, so for this assignment, we're looking at recent data, and there's a file available. This was from Sunday's forecast, and there's sample code available on the class webpage. Okay, so if you look at the link under the 433 page here, it says Lab 5 code. This is basically what you need to go through for this lab. And we're going to use a Python notebook for this. Okay, and so I'm going to ask you to turn in your notebook and make sure that it contains all of these things on this checklist. Okay, so print a list of variables from this GFS file, print the dimensions, read in the heights and the temperatures, print the max-min values on different pressure levels, latitude, longitudes, make a basic contour plot, print out the longitudes, make a nicer contour plot using the CartoPy package, save an image, upload it to Blackboard, save your notebook, download the notebook and then upload that to Blackboard. So most of this is just getting used to the Python, but we're going to focus on the momentum equations in this lab. And this is what we spend most of our time talking about in dynamics classes. So these are based on F equals ma, Newton's second law. Typically for air, we consider air parcel and a unit mass, so we divide both sides by m, and this really gives an equation for the acceleration of a parcel of air. So that acceleration is going to be the net force, and the forces that act on air parcels are pressure gradient force, Coriolis force, gravity, and friction. And if we stick to analyzing, say, the mid-troposphere, so we get above the surface, we can assume that friction is small, so we usually neglect that. And if we just consider horizontal motion, gravity won't be explicitly found in the forces. So we're really looking at the Coriolis force and the pressure gradient force in our horizontal momentum equations. Pressure gradient force will accelerate from high to low, right? So parcels will be accelerated towards lower pressure, and that's the same thing as lower heights on a constant pressure surface. So we're going to look at these equations using pressure as our vertical coordinate, and when that's the case, the pressure gradient force is actually a height gradient or a geopotential gradient. And then the Coriolis acceleration, the Coriolis force will deflect our parcels to the right as they move if we're in the northern hemisphere. Okay, and so we can write those equations like this. So du dt, that's the total derivative. This is the acceleration in the x direction. And we have the Coriolis acceleration as the first term, F times V, and then the pressure gradient force is the second term. And same thing in the y direction, dv dt is our acceleration in the y direction. We've got minus F times u, F being the Coriolis parameter, and this is the Coriolis acceleration. And then the pressure gradient force is minus g dz dy. Well, like we did before, we can expand the total derivative and rearrange the terms in order to get an equation that is written in terms of the local rate of change, right? The local time tendency of the u and v parts of the wind. So this, if we were to be interested in forecasting things from a local perspective, these are the equations we'd want to use. And just like in the thermodynamic equation, we have a horizontal advection of momentum this time. So minus u du dx minus v du dy is the horizontal advection of the u part of the momentum. And then minus omega du dp is the vertical advection term. And then we have the Coriolis acceleration and the pressure gradient acceleration. And so these are the terms of the both of these equations. It's just different directions for the change in the momentum. So we have an x direction equation du dt, and we have a y direction equation dv dt. Well, we know that we have this concept of the geostrophic wind and geostrophic balance. where if we don't have any acceleration on these equations, the left-hand side 0, and the wind that satisfies this balance between Coriolis and pressure gradient forces is what we call the geostrophic wind. Well, if we plug in for our values of the U and V components of the wind, the sum of the geostrophic and the not geostrophic, or what we call the ageostrophic wind, the geostrophic part of the wind and the pressure gradient force will cancel each other out. So these momentum equations simplify to basically one term. We have the acceleration on the left-hand side is equal to the Coriolis parameter times the ageostrophic wind on the right-hand side. And these results show that the ageostrophic wind points to the left of the acceleration vector. At least in the northern hemisphere, that's the case. And this is the, in words, the frictionless momentum equation using pressure as the vertical coordinate. So we can use this to understand how the ageostrophic part of the wind is operating if we can understand the acceleration of the flow. And acceleration can occur if the winds are turning, right? Either turning to the right or turning to the left, we have an acceleration, or if they're speeding up or slowing down, in the same direction. So this helps us to diagnose things like jet streak circulations in the 4-quadrant model. Also to explain why we have supergeostrophic flow and ridges, subgeostrophic flow and troughs. It basically comes down to this simple relationship between the acceleration and the ageostrophic wind. So we're not going to focus on doing calculations of these terms with this lab, but we can do a lot of the same things that we did in Lab 4 with the same methods and calculate the advection, calculate the different forces just by looking at the data on the maps and doing finite difference approximations. Well, what we want to do with this lab is basically go through the checklist and make sure that we can do all these things, and this code that I put on the class webpage basically goes through those steps. And so to use the Python notebook, you want to do a search on Scholar, RCAC, and Purdue, and go to the first link. And we want to use Jupyter Hub. Okay, so this launch button on the Scholar page will start Jupyter Hub. This remote desktop is what we used in Lab 3 to do the thin link. So we're going to use Jupyter Hub. So I'm clicking on this, and you can see it's running Jupyter. So this is basically a Python notebook interface through a web browser, which is really nice to have. So I'm going to log in with my career account, and I'm not going to save that. And so yours is going to look different from mine because I've got a lot of things that I've run on here. But basically, it should show you a list of the directories and the files that you have in your home directory on the Scholar cluster. And this is how we can start running a Python notebook. So what we want to do is click on New and start a new notebook. So the Baldwin EAPS Python 2 will be what we want to use. So this has things set up so that we'll be able to use some of the software packages for our weather data. If you pick that, it's called a kernel. It's basically the version of Python that we're running. So Python 2, actually 2.7 is what we're running here. And the way this works, you can type in code, and you can execute the code by hitting Shift-Enter. And it basically will try to run the code, and if there's an error, it'll say so. And you can sort of interactively run through Python code in this notebook. You can save the notebook. You can download the notebook, okay, and you can close it when you're finished. I'm going to rename this to something that's more useful for this particular lab, Lab 5. And then I'm going to go back to this web page that we have on Extreme Weather Makers that has this sample code. Okay, so all this is fairly small. I'm going to increase the size so you can see this. And basically this stuff that in these blocks, you should be able to just copy, just highlight with the cursor, hit Control-C to copy it, go over to your notebook and hit Control-V to paste it. If that doesn't work, you just need to type these things in just as they're listed, and then Shift-Enter to run it. So you can see there's a little asterisk, and then that turns into a number. When it's an asterisk, it's trying to run the code. It's like thinking. When it's done, it turns it into a number. It basically tells you which step you're at in your code. So step 1, I tried to run this, it didn't work. Step 2, I ran these commands, and then they seem to have worked. So the way Python works, you have to import different packages that you want to use. So we're going to import NumPy. It's a very powerful numerical Python package that has a lot of mathematical functions and arrays that we're going to use a lot. Matplotlib is for doing plotting, and there's a pyplot package that we're going to specify specifically as PLT. So whenever you import something as something else, it basically is an alias, and we can shorthand that, just refer to it as PLT in our code. Then we're going to use Cartopy for the cartography to do the maps, basically. And this is another nice Python package to make nice looking maps. And then NIO, N-I-O, is for the I/O. It's for input output. It's for dealing with the weather data in the formats that we have. And so our data is from the GFS in GRIB2 format, and this NIO allows us to deal with that very easily in the Python code. So the next block of code actually will read in the file that we're interested in this lab. So I'm just copying and pasting. The file name is given as a string, and strings in Python have to start and end with quotation marks. So this is the actual name of the GFS file. And then you can see I'm going to refer to the NIO package, and whenever you have something that refers to one of these Python packages, you use a dot and then some function that goes along with it. So we want to open a file using NIO, We use neo.open underscore file, and then the file name, and then R as a string means we're just going to read it. And that's going to be assigned to this object gr, so that anything that we refer to from now on in terms of gr is going to be dealing with this file that has been opened by Neo. Okay, so there's a lot of things going on there. But basically, this just reads in the file. And now we can start to manipulate that file. So the next block of code I'll execute that. It sets up a variable names. It sets it equal to gr.variable.keys. So remember, gr is this object up here. It's just the open file. And then we want the variables and the keys for all of the variables that are in this file. And then I'm going to print those. So this print statement just prints the variable names, okay, the string, and then the variables. You know, this names variable that has all the variable names that have been decoded by Neo. And so here's what we get as a result. So it's pretty messy. There's lots of different sort of codes that are involved here. Hopefully some of these are making sense, like HGT is height, VVEL, vertical velocity, UGRD is the U part of the wind, here's RH, relative humidity, here's temperature, TMP, here's dew point, there's potential temperature. So it's all code, and you know, there's a big table to try to decode these variable names. We're going to be sticking with things like temperatures and heights for this lab. You can see the grid dimensions are assigned to this variable dims. So this next bit of code is just setting to print the dims. And this shows you, just type this in, how many points there are. Longitude, there's 720, and vertical levels, there's like 17 vertical levels. Latitudes, there's 361. So it basically gives you the size of the grids, both horizontally and vertically, for these different variables. Okay, so it's a latitude longitude grid. There's 361 different latitudes and 720 different longitudes. So that works out to half a degree in latitude and longitude in terms of the grid spacing. So the next block of code shows you how to read specific variables and assign them as arrays. And so HGT is what we're going to set equal to GR variables and then this particular variable name. Okay, so that variable name's in quotes because it's a string, and it's one of these from up here. Okay, it's height underscore P0 underscore L100 underscore GLL0. Well, I'm going to read that in and assign it to HGT. And this little bracket with the colon means I just want all the numbers. And same thing for the temp. The only thing that changes here is TMP. And so these are basically the three-dimensional heights and temperatures for this global grid that now we can refer to with these arrays that we've called HGT and temp, TMP. So now we can start to use the NumPy functions to calculate useful things from these, arrays. And so I'm showing you an example of the mean, the max, and the min. These are NumPy functions. So np.mean is using the NumPy mean function. And whatever is inside the parentheses is what it's going to try to find the mean of. And it's trying to find the mean of the heights. And the height is a three-dimensional array. So the way Python deals with that is with the brackets. We can refer to a particular level, vertical level, level 30. So they're dimensioned as the number of vertical levels, and then the number of rows, and the number of columns in the 2D grid. If I use a colon, that means I want all of them. So I want all the rows and all the columns, but just the 30th vertical level. And that gives me the mean, the max, and the min of this particular vertical level. Okay, and this one happens to be the 1,000 millibars. Okay, there's 31 vertical levels for this particular grid, and we might also want to look at level 25. Okay, so we can basically just change these 30s to 25 and shift enter that code and see the mean, max, and min on level 25, which I happen to know is the 850 millibar level. Okay, so that's how we can refer to parts of the three-dimensional array using the NumPy functions to do useful calculations just with a couple lines of code. All right, so I'm going to read in the latitudes and the longitudes. That's what this next block of code does, and turns those into 2D arrays using the NumPy mesh grid function. If you've used MATLAB, there's a similar function in MATLAB to set up a mesh. And we need these so that we can plot the data, and we can have our 2D heights and temperatures map to 2D latitudes and longitudes and be able to make a nice map. All right, so let's just pull one particular level, level 25, for the height, and assign that to a new variable we call height 850, and do the same thing for the temps. So temps C850 are the temps at level 25. It's giving us all the rows, all the columns, so those all of the different longitudes, all the different latitudes. But I'm subtracting off 273.15 to convert it to degrees C. Okay, so that's, you can do that just one line of code. Okay, so now we can do a simple plot, and we can use that matplotlib plot command and do a contour plot. Okay, so if we just do plot.contour and then in parentheses height 850, we just get this simple map of the 850 millibar heights all around the globe. Okay, you can see there's 720 rows and there's 361 columns. So the rows are different longitudes and the columns are different latitudes. So this is just a global, really simple plot of the 850 heights. There's no contour labels on here. It's hard to know exactly what we're looking at. But this is just a really quick, easy way to plot contours. So we can do the same thing. We can change this and plot the temperatures at 850 and get a similar map. Well, we probably want something a little bit more useful and something that will show us, say, the background geographic maps. Shows us where the states are, shows us where land and ocean is. Something we can set, the exact part of the world we want to look at, and something that will label the contours for us. So that's what this last block of code does. And I'm just going to copy it and paste it and execute it. And you can see what we end up with. So this is hopefully looking more familiar. You can see we've got our US background map. The contours are in red and they're labeled. So 1470, 1500. So this is the 850 millibar heights, basically zoomed in over continental US. And you can see this is the Python code that we need to generate that map. So the first step, we're defining a figure of a certain size, and then we're setting up what's called a subplot. And we're using this map projection that's part of CartoPy that does a Lambert conformal map projection. It makes this nice looking map underneath. And we're going to add features to that map. Okay, land, ocean, coastline, borders, lakes. And so you can see it's making the land and the ocean different colors. The lakes are another color. The actual borders are dashed between the US and Canada and Mexico. And then we're using this natural earth to get the states and the provinces, and we're adding those features. So we get the state boundaries on there. The levels are just the contour intervals for the heights, and then the set extent basically gives the longitude and the latitude limits for the map. So we're plotting between -120 and 70 longitude, so it's degrees east. Negative would give us degrees west, and between 20 and 50 degrees north latitude. So you can change those around and see how that changes your map area. And then this contour, we'll do the contour plot. So we have to give it the longitudes, the latitudes, and then what we want to contour, the height at 850. The levels specify the contour intervals. Okay, so that's using this arange function. And arange just does a list of values that start at this number and end at this number and increment every 30. So we have a 30-meter contour interval. Red colors. It's another thing to be easy to change. And we have to use this transform to go from our latitude longitude grid onto this Lambert conformal map. So this plat carré is the latitude longitude transform. Once we have that, we can label the contours. That's what the C label does. And we can control the font size and the format of those contour labels. So that's how we get this nice looking map. Now we might want to save this image, so we can right click on it. We can just open it in a new tab, or right click and save it as a file, and then upload that to Blackboard or a web page, whatever we need to do. And those are the basic. There's a couple of things on the list of the checklist here, but basically that's what asking you to do, and to get some familiarity with Python notebooks, and using Neo, using Matplotlib, and using Cartopy to make some nice plots. So you might try changing the map area around, the extent. You might try changing from 850 heights to 850 temperatures, changing your contour intervals, levels here, and try to make your own custom map. So when you're finished, you want to save and checkpoint. So that basically will save your notebook so you can come back to it later. And you want to download your notebook as a notebook. So this is going to download this in your downloads directory, and then you can insert that into the Lab 5 Blackboard assignment to turn this in. Then when you're done, you click Close and Halt. Now close that window, and in the main Jupyter Hub, just click Log Out, and that'll get you back to the login page. So basically that is all we need to do for Lab 5. And again, that code is on our class webpage under Lab 5 code. So let me know if you have any questions.